Okay, for what we have in number 20, okay, we have an exponential equation that has unlike bases, and there will be unlike bases that share no common base. Here we have 5 to the x plus 2 is equal to 18, and for what we have in x, we have only on one side of the equation, and what I can do here is I can write the left-hand side in terms of x plus 2. So what I can do here is I can get rid of the exponential base 5 by taking a base 5 logarithm. And I'm going to take the base 5 logarithm of both sides. So I have the base 5 logarithm of 5 raised to the x plus 2 is equal to the base 5 logarithm of 18. Okay, so left hand side we're going to have at x plus 2. And for what we have in the case of the base 5 logarithm of 18, I can either use base 10 or natural logarithms, and I'm going to utilize the change of base formula. So I'm going to have with the base 10 logarithms, we have the base 10 logarithm of 18 over the base 10 logarithm of 5. And so we have for this ratio, okay, so for what we have for the base 10 logarithm of 18 over the base 10 logarithm of 5, I would have the same result if I had applied natural logarithms. Okay, so we have in this particular case, right, so we have x plus 2, and you have equal to about 1.97959 something, and taking away 2 from both sides, and so we have to about the nearest 3 decimal places. Okay, x will have right at minus 0.204. For number 21, we have the reappearance of the exponential base 5, and this time we have raised to the x minus 1, where we have 5 to the x minus 1 is equal to 3. And again, I can free up x minus 1 by eliminating the exponential base 5 by taking the base 5 logarithm of both sides. So we have left-hand side, we have at x minus 1. And for the base 5 logarithm of 3, okay, I can once again use base 10 logarithms, but I'm just going to use natural logs this time around. Okay, so we have in this case, all right, so we have that x minus 1, okay, is equal to the natural logarithm of 3 all over the natural logarithm of 5. And we have, in the case of approximating, okay, so we have x minus 1, and we have it equal to 0.6826. And if I add 1 to both sides, okay, we have x rounded to the nearest 3 decimal places. It will be right at 1.683. Okay, for what we have in number 22, okay, we have the appearance of x in the exponential position present on both sides of the equation, and it's not going to be to any advantage to use base 4 or base 18 logarithms. Okay, and we have here, under these circumstances, think about, like, in a sense, almost what arguably might be using the change of base formula earlier, where we applied natural or base 10 logarithms. And we'll say that we have, for this case, all right, what I'm going to do here is I'm going to take the base 10 logarithm of both sides, and here, okay, for x plus 1 and x minus 3, okay, we can treat the powers and re-express as binomial coefficients. Okay, so I'm going to have left-hand side, I'm going to have all of x plus 1 times, okay, the base 10 logarithm of 4 is equal to, and we have all of x minus 3 quantity times the base 10 logarithm of 18. Now, if I go ahead and distribute, okay, so we have x plus 1 multiplied by the base 10 logarithm of 4. We have x times the base 10 logarithm of 4 plus the base 10 logarithm of 4. And we have is equal to x times, okay, the base 10 logarithm of 18. And we have minus 3 times the base 10 logarithm of 18. And for what I have here, I have a couple of x terms with the base 10 logarithmic terms attached. And I have just constants that are in the form of logarithms in base 10. And what I'm going to do here is I'm going to go ahead and combine the x terms. Now I can either take away x log 4 or x log 18. And at the same token, I'll just have the x terms on one side and constants in the base 10 logarithm on the other. So I'll just move the base 10 logarithm of 4. And we have, upon gathering, and we have x times the base 10 logarithm of 4 minus x times the base 10 logarithm of 18. And we have is equal to minus 3 times the base 10 logarithm of 18 minus the base 10 logarithm of 4. And we're looking at solving for x. So if I look at factoring out the x, we have x times the quantity of the base 10 logarithm of 4 minus the base 10 logarithm of 18. Again, we have equal to minus 3 times the base 10 logarithm of 18 minus the base 10 logarithm of 4. And we have, upon isolating x, again, we have a quotient, and we have minus 3 times the base 10 logarithm of 18 minus the base 10 logarithm of 4. And we have divided by, okay, the base 10 logarithm of 4 minus the base 10 logarithm of 18. And just expanding on out. Now, if you have a scientific calculator, okay, and now this is going to be order of operations sensitive. And you have like minus 3 times base 10 logarithm of 18 minus the base 10 logarithm of 4. Notice all the parentheses here. Okay, so I'm going to put in parentheses the difference that I have in the numerator, and I'm going to have divided by, and we have also in parentheses, we have the difference between the base 10 logarithm of 4 and the base 10 logarithm of 18. Okay. And if you were to key this in, okay, and you would have, okay, to about the nearest 3 decimal places, and we have for the result, x will be about 6.687. Okay, for what we have in number 23, we have e to the x plus 1 is equal to 14. Okay, so in this one, you can have x on one side of the equation, and the base, exponential base, is e, and this is just going to be a natural logarithmic exponential base. And if I take the natural logarithm of both sides, we have natural logarithm of e to the x plus 1. This will go to x plus 1. We have is equal to the natural logarithm of 14. And again, for the natural logarithm of 14, okay, you have among the first digits, you have 2.639057. And if I take 1 away, okay, to the nearest 3 decimal places, we're going to have, for x, okay, you have about 1.639. All right, for number 24, okay, we have x present on both sides of the equation, and you can apply either natural or base 10 logarithms. Okay, now my inclination would normally be to go with natural logarithms, and I would, but I'm just going to show you from the base 10 logarithmic perspective. Okay, so if I take the base 10 logarithm of both sides, okay, now base 10 logarithm and e don't match, base 10 logarithm and 3 don't match, but I can make the x minus 2 and the x plus 1, again, as binomial coefficients, as was the case in problem number 22. So we have x minus 2 times the base 10 logarithm of e, and I have is equal to x plus 1 times base 10 logarithm of 3, and just taking what we have and distributing. So I have x times base 10 logarithm of e minus 2 times the base 10 logarithm of e, and we have is equal to x times base 10 logarithm of 3, and we have plus base 10 logarithm of 3, and I can combine the variable terms. Okay. So I just take away base 10 logarithm of 3, or x times base 10 logarithm of 3, and add 2 times base 10 logarithm of e, so we have enjoining, so we have x times base 10 logarithm of e minus x times, okay, the base 10 logarithm of 3, and we have is equal to the base 10 logarithm of 3 plus 2 times the base 10 logarithm of e, and solving for x, now we have in factoring, so I have x times the difference between the base 10 logarithm of e and the base 10 logarithm of 3. And again, we have equal to the base 10 logarithm of 3 plus 2 times, okay, the base 10 logarithm of e. And in isolating x, so I'm going to take the sum on the right hand side of the equation and divide by the binomial coefficient, where we have the difference between the base 10 logarithm of e and that of 3. Okay. Now, so we have, in the case of x, and just putting this in calculator terms, okay, so I'm going to quantify the difference, or I should say the sum, in the numerator. Okay. And we have divided by, and we have the quantity, okay, you have the difference between base 10 logarithm of e and the base 10 logarithm of 3. And taking what we have to the nearest 3 decimal places. Okay, so we have to the nearest 3 decimal places. This will come out to about a negative 31.422.